Hey everyone, Mr. Shatter here to take a look at logarithmic differentiation, which is going to be a tool used to calculate derivatives of functions we've yet to be able to calculate the derivative of. I promise at the end of this video there won't be a function you will not be able to differentiate. We've learned a lot of rules so far. Let's go ahead and finish up with this last one. Here's a function that at this point we haven't really learned how to take the derivative of it. We've learned how to take the derivative of e to the x. We've learned how to take the derivative of a to the x, which is not this, because this has a variable base and a variable power, whereas a to the x is by definition a constant base. So it's not like that either. We know how to take the derivative of log base a of x, so on and so forth, but we really haven't ever learned how to take the derivative of a variable raised to another variable. So in this example, we're going to use a technique called logarithmic differentiation. Now, logarithmic differentiation is essentially just like implicit differentiation. In fact, it even uses implicit differentiation. But the purpose of it is to get logarithms in the problem in order to differentiate implicitly. Well, what I mean is, in order to solve this problem, we're going to actually take the natural log of both sides. Okay? So we're going to take the natural log of y and set it equal to the natural log of x to the x power. And then using a property of logs, we know the exponent on the logorand can actually come down and become the coefficient. So this is going to be the natural log of y is equal to x times the natural log of x. All right? Now I've got a problem. Again, I haven't differentiated yet. I just simply took the natural log of both sides. Now I'm going to differentiate. So I'm going to take a derivative. So I'm going to note that I'm taking a derivative. The derivative of the left side is the derivative of a natural log, which we know is 1 over u times du dx, which in this case would be dy dx because it's a y. And then on the right side, I actually have to use the product rule. So it's going to be first times derivative of second, which is 1 over x, and I could tack on a dx dx if I wanted to, but it's not necessary because I know that's just 1, plus the second function times the derivative of the first. Well, on this side, it's just 1 over y dy dx, but interestingly enough, and we'll just rewrite it, 1 over y dy dx. Interestingly enough, the x and the x end up canceling, giving you just 1 plus ln x. Multiply both sides by y. Multiply both sides by y. So this is going to be dy dx, which is what I want, is equal to y times 1 plus ln x. And last but certainly not least, I actually have an expression for y. If I go up to the top and I look, y is equal to x raised to the x. So put it back. So dy dx at the end is going to equal x to the x times 1 plus ln x. And this is my derivative. So this is a technique used to take the derivative of something we have yet to learn how to, using implicit differentiation of logarithms, which we conveniently call logarithmic differentiation.